C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
All right, good day, folks. We'll be getting started with the webinar here shortly. Just getting a few more minutes here to let some folks join through the registration process. A few housekeeping items just to go over for the folks who are currently on the line. Today's session will be recorded and available as a playback after the end of today's session. So if you perhaps have to drop off early, or if you have some colleagues that maybe weren't able to make it and you think this would be interesting for them, you will be able to review the content after today's session has concluded. I'll also make just note of the Q&A feature. So as we are going through today's session, if you do have any questions related to the content that is presented, maybe it's something related to work that you're doing or just anything that was shown here today, please feel free to make use of that feature. We will reserve some time at the end of the session to go over those questions together. Okay, so that all being said, I think we are a couple minutes past the top of the hour, so we can go ahead and jump into it here today. So welcome, thank you for joining today's webinar. My name is Aria Hakimian. I'm an application scientist here at C-Therm Technologies. Today, we're excited to have a special guest speaker, Dr. Alina, who will be joining later to talk about some of her work in heat transfer fluids, specifically looking at the thermal conductivity of nanoparticle-enhanced fluids. So I'm going to start out with just a little bit of a general introduction to get things started, and then I'll be joined by Dr. Alina here shortly in a few minutes. So for those of you that may be new to C-Therm, just wanted to give you an overview of who we are, what we do. So we are primarily focused on thermal conductivity, specifically through the advancements of transient-based methods for this analysis. Really, our goal is to simplify thermal conductivity testing for the materials of tomorrow. Now, here at C-Therm, our core product is called Trident. So you can see this on screen here. Trident was developed as a modular platform. So it brings together multiple methods for thermal conductivity characterization. Really, when we're looking at the measurement of thermal conductivity, the best technique or the best option really depends on the sample that you're looking at, maybe the conditions that you're looking to represent in your testing. And that's why it's, as you can see here, it's better to have options. Being able to pick and choose the best tool for the task at hand is ultimately going to lead to the best overall data, the best quality of results. And the whole idea behind Trident, it stems from this quote here. We like to use this one to kind of demonstrate the value. But when all you have is a hammer, everything looks like a nail. This is a quote from Abraham Maslow, but it really embodies the idea behind Trident. Again, being able to pick and choose the best option for the specific scenario is going to lead to your best possible outcome. Now, for those that may be new to thermal conductivity, or maybe you've been in this space, but you're trying to see what options exist out there, we do have a method selection guide. This is available as a free download through the links that my colleague Engad is posting in the chat, as well as on our website. So if you'd like to kind of get an understanding of what methods exist in the space, both the ones that we offer here at C-Therm, and then, of course, others that are available in the industry, this is a nice free resource just to kind of get a run through of what options exist depending on what you're looking to measure. So definitely recommend checking this out if you're looking for more information. I'll also just make a note here that, so C-Therm, as I mentioned, we are leaders in thermal conductivity, transient thermal conductivity analysis, but we are also partnered with Rigaku as well as Metrovib in North America for their line of thermal analysis and DMA instrumentation, respectively. So if you're looking for other material characterization outside of thermal conductivity, these are certainly areas we're able to assist in. Also, our thermal analysis labs team, this is our contract testing division here at C-Therm. We offer contract testing for all the instrumentation that we offer, all the methods that we have here at C-Therm, as well as others in the industry. So maybe you're not necessarily ready to bring an instrument in-house, but you are looking for a group to do some testing for you, we're certainly happy to support in either scenario. And I'll just end kind of the general introduction here with a client testimonial. We always like to share different, what folks are saying about their experiences with C-Therm. I picked this one here from Honeywell. Very distinctly to the point, but the system is very easy to use and provides fast measurements. This was from Eric Eastwood, who is a principal R&D scientist at Honeywell. Now, if you'd like to see maybe what some other folks are saying, we do have a list of testimonials available on our website. Again, just another resource you can take a look at to see what types of people are using the device, what they have to say about their experiences with us here at C-Therm. Now, before I pass it off to our guest speaker here today, I just wanted to do just a very brief introduction in terms of the topic today. So, starting out with thermal conductivity, again, this may be review for many folks, but just to make sure we're all up to speed, what is thermal conductivity? Well, thermal conductivity describes a material's ability to conduct heat or transfer heat. When we look at it here in terms of the units, we'll be referring to the standard SI units, watts per meter Kelvin. But this is the rate at which heat flows through a substance per unit of temperature difference. Oftentimes, of course, thermal conductivity is a critical performance metric in a variety of applications where we have to worry about the amount of heat being generated in a system, and of course, the materials that are introduced to help alleviate some of that thermal stress on the device or the system in question. Now, specific to today's topic of heat transfer fluids, liquid testing, one thing I always like to just put out there and make sure folks are aware of is the impact of convection. Convection is another form of heat transfer that can occur in a material. And one of the things to keep in mind is if you are looking to measure thermal conductivity, but there's convection introduced into your system, this can result in a bias. So convection is something we always want to essentially eliminate in terms of doing a thermal conductivity test in order to get the best possible results. And there's a few ways we can address this, but specifically on the Trident platform, I just wanted to give you really the overview of what options are most recommended for non-solid materials. And really there's three here. So there's the MTPS, which will be featured in some data later here today, but there is also the transient line source and THW. So these three methods are great options for liquids in different scenarios, right? Volume requirements, as far as those go, the MTPS, as you can see, does offer some of the smallest possible volume based requirements for testing. This can be really useful in scenarios where maybe you only have a very small amount of material available. Of course, the TLS and the THW, you can see there's much more material required. But again, depending on the use case, this may or may not be a major consideration, but it's something to be aware of. I was mentioning convection earlier, and one thing that really helps dictate if this is going to significantly impact the measurement is the duration of the test. Typically, one thing that is done in order to mitigate convection is using a very short test time. And as you can see, both the MTPS and the THW have very short test times. They're typically about 1 second in duration. Now you'll notice the TLS here, are on the minutes time scale. So while the TLS is usable for fluids, typically it's recommended for higher viscosity fluids where this impact of convection is less significant. If you are dealing with more aqueous-based solutions, low viscosity systems, really the MTPS and the THW would be the two best options to consider in that space. And then you can see some other details like on the temperature range capabilities, some of the standards that these methods conform to, etc. So, not to belabor the point any further, I just want to share, as I mentioned, the THW is one option that exists certainly for the testing of thermal conductivity of fluids. We're not going to go really deep on this here today, but I did just want to share an example data set. So, if you were ever dealing with like glycol, glycerin, water-based materials, again, the THW here is certainly one option that can be used to test these samples. The ASTM D7896 is one that we do see referenced quite a bit for a variety of coolants. There are scenarios, of course, where groups are really looking to conform to a specific standard, and the THW does check that box for some folks. But again, we also have the MTPS. Now, as we can see with the MTPS here, just a flat sensor surface, active area of the sensor itself is about 18 millimeters in diameter. Now, the MTPS is also capable of testing testing solid materials as well, which is what this kind of setup would dictate. But if you're looking to test a non-solid, a liquid, a powder, or a paste, then we do have the liquids and powder cell shown here. Very simply, a nice just metal attachment that pops onto the sensor, and you can see you can fill that with the non-solid material of interest for testing. So in either scenario, there are a couple different routes. Again, which one is the best one really would depend on the specific samples you're looking at, the conditions you're looking to test under, etc. But I just wanted to maybe give a little bit of a quick overview of what options exist there on the Trident platform for testing liquids. But at this point, that kind of brings me to the end of the my introduction here. As I mentioned at the beginning, we do have a guest speaker here today who will be taking us through the remainder of the content. Dr. Alina can join us on screen here. I'm going to stop sharing. She's going to take us through some of her work in the heat transfer fluids and looking at the thermal conductivity measurements using our Trident system. So with that being said, I'll stop sharing here and invite Dr. Alina on screen.
Hi, everyone. So while I'm sharing my screen, thank you for being here. Okay, I think that now is okay. Can you confirm me, Arya?
Yep, it looks great.
Oh, okay, thank you. So hello, everyone, again. Thanks for being here for my presentation about evaluating the thermal conductivity of nanoparticle-enhanced fluids. I am Alina Minea from Gheorghe Asachi Technical University of Iași from Romania, and I work in new nanoparticle-enhanced fluids for over 15 years. So here you can see in this slide, I wanted to show you a short biography, and it was mentioned that I was involved in the first and the only cost action dedicated to nanofluids. The cost action was called Nano Uptake, that managed to make a big step forward in the nanofluids area by an European-wide cooperation together with Canada, United States, and Brazil. So today I will talk shortly about the concept of nanoparticle-enhanced fluids and associated mechanisms, followed by several experimental results on ionic liquids and polyethylene glycol-based fluids, about thermal conductivity, and a little bit about effusivity. By the end of the presentation, I will also show you a few ongoing experimental and lab facility, as well as our current project. So I will just start about nanoparticle-enhanced fluids for those who are not familiar with this concept. That was not a new concept. Actually, it's a term that was firstly coined by Choi in 1995, so there are some years ago, to describe this class of nanotechnology-based heat transfer fluids that exhibit thermal properties superior to those of their host fluids. The idea was to add solid nanoparticles to existing fluids, existing heat transfer fluids, with the aim of increasing the thermal conductivity of the fluid itself. So this technology, even if its roots are about 30 years old, it is still at the beginning, since the most of the nanocolloids are at a technology readiness level of about 3 to 4. Anyway, there is a large debate in the literature based on thermophysical properties of nanocolloids, method of approach, validity of applications, and a lot of equipment that are suitable or not suitable to estimate these heat transfer fluid thermophysical properties. So, as was outlined in the open literature, the research nowadays is directed to simple nanofluids, hybrid nanofluids, as well as other nanofluids based on different bases like molten salt, refrigerants, ionic liquids, and polyethylene glycol-based nanofluids. Today I will talk a little bit about nanofluids that are based on ionic liquids and polyethylene glycol, liquid bags, not the ones that are used as phase change materials that are with a higher mass. These two kinds of nanofluids are fluids with higher viscosity. I will not say very, very high, but it is much higher than the viscosity of water. So my group experimental work over the years was focused on several host fluids. Of course, we started with water, like everyone. And after that, we tried to use ionic liquids. We considered two of them. The first one was 1-ethyl-3-methylmidazoleum metanosulfonate. That was more viscous than the first one that is written there, that is methylmidazoleum tetrafluoroborate. We tried also a mixture between ionic liquid and water that decreased the viscosity, and later we tried to check on PEG 400 and PEG 200. We used several nanoparticles with surfactants. We made also nanofluids without surfactants. We have a lot of results and suspensions that we manufactured over the years. So it is nice to emphasize that the work outcomes were in 3, I think now there are 4 PhD theses that 3 are defended. One is in the course of defending. 1 postdoc, 2 national grants, and over 75 papers in the last 10 years. So these are the results of my research group in nanofluids. I will start with the basis, not much. I just want to outline that nanofluids preparation methods are 2. The single-step method and the 2-step method. They are outlined in this slide. Well, the 2-step method is the most widely used since it is the most economical one, and it can produce nanofluids in large scale because nanopowder synthesis techniques have already been scaled up to industrial production levels, so it is much easier to use the two-step method. Also, it is easier to have some control on nanoparticle size, also on further stabilization methods. So the methodology, it's not that simple as one may think, that we take the liquid, we take the nanoparticles, we mix them together, and here we are. It's not that simple, but I may say that it's not that complicated, but one have to be very careful in order to have control over the experiment and over the properties at the end. So the methodology implies the mixing process of base fluid and nanoparticles, while here you can see a few steps starting with weighting of the, you need very good equipment in all the phases. Sonication, we have several methods for sonication. You can see here also several of our recent suspensions. And of course, it is the C-Therm equipment that we employed for thermal conductivity and effusivity tests. Further, I will discuss shortly on the mechanisms of thermal conductivity enhancement. So the thermal conductivity enhancement was found actually to be due to the addition of high conductive nanoparticles into the base fluid. So acknowledged mechanisms in the open literature are Brownian motion, surface charge, liquid solid interface layer, nanoparticle clustering. So actually the last one is not what we want to have in a nanofluid. We don't want clusters because they will sediment. But Brownian motion is the most credible one and seems to be the most accepted by all of the researchers. Anyhow, a number of questions are still unanswered in regard to the main cause for this phenomenon. So several aspects that have to be clarified in the next steps of research is the influence of the base fluid, especially if it talks about ionic liquids, and of the nanoparticle type and shape in order to tailor a better heat transfer fluid. I will just, I inserted here a slide on a specific heat or isobaric heat capacity with some researchers' analogies. So I inserted this because we are trying to measure it and also to work with it on both sides using a DSC and also using the formula from thermal effusivity that effusivity is measured also by the C-Therm equipment. In regard to specific heat results, these are somehow contradictory and highly dependent on the base fluid. So based on the previous reports on the simple molecular solvent-based nanocolloids, the mechanisms of heat capacity in enhancement of EO nanofluids is probably driven by the existing interfacial nanolayering occurring on the surface of nanoparticles. Some other studies reported the possibility of mesolayers overlapping as a mechanism of variation of specific heat for nanocolloids extended also to the ionic liquids with nanoparticles suspended. The specific heat is highly dependent on the base fluid, and there is no, let's say, a common trend. In some cases, the specific heat increases with the addition of nanoparticles. In other cases, decreases with the addition of the nanoparticles. So in this second part of the presentation, several experimental tests will be discussed, and I will start with the experimental on ionic liquids-based nanofluids thermal conductivity. The results are recently published, actually last year, in International Communication in Heat and Mass Transfer, and involved 1-butyl-3-methylmidazolam tetrafluoroborate ionic liquid and 3 kinds of nanoparticles as are shown in this slide. So we used alumina, zinc oxide, and the very known multi-wall carbon nanotubes. So the properties are in this slide, but more interesting is that very low amount of multi-wall carbon nanotubes added to the ionic liquids get very nice enhancement in thermal conductivity if compares with the base ionic liquids. So Actually, it's not surprising because if it compares the thermal conductivity of the three kinds of nanoparticles, the multi-wall carbon nanotubes have the highest thermal conductivity if compared with the other two. We measured also the variation of thermal conductivity with the mass concentration of nanoparticles, and you can see that the thermal conductivity linearly increased with the addition of nanoparticles, which is a normal phenomenon. So the highest increase was due to alumina addition to the ionic liquid. Here is the variation with temperature. We measured the variation of thermal conductivity with temperature up to 60 Celsius degrees. And you can see here the different behavior of different kinds of nanofluids, nanocolloids, and also that the thermal conductivity tends to be constant for lower additions, but it increases with temperature, and the highest increase is for 1% alumina addition. As a conclusion on this experiment, it can say that the thermal conductivity of the ionic liquid is not influenced by the temperature variation, and all the Niels thermal conductivity varies with nanoparticle concentration, and this increase is linear. The thermal conductivity dependency on temperature on temperature, you can see that low concentrated suspension follow the trend of the ionic liquids, while higher loads of nanoparticles go to a polynomial enhancement in thermal conductivity. Go to the other part to present the tests, the experimental on polyethylene glycol-based nanofluids thermal conductivity, also with two oxides this time. Of course, we have some more experiment, but I chose this one. I don't know why. I just picked them from all the experiment. So here we will see the two nanofluids based on polyethylene glycol 400. Yeah. And also I want to discuss a little bit about different equipments. When we started the experimental, we asked a colleague to perform some thermal conductivity measurement, and the colleague had a KD2 Pro, and also using the KD2 Pro was also in a laboratory in Spain with data provided by Marcos et al. And I can say that also nowadays the most employed equipment for thermal conductivity measurement is KD2 Pro. Usually I'm not encouraging this kind of measurement, and it's not because I am biased. It is because the KD2 Pro have a accuracy of plus minus 10%. So this is rather high because in some cases there are authors reports thermal conductivity enhancement of 5%. So it cannot be accurate because it is within the accuracy limits. So after we purchased the C-Therm equipment, we were able to compare better and to obtain more trustable results in thermal conductivity. Also, this is not only our opinion, because this opinion was published also some years ago in 2016 by Antoniadis. You have the reference here. It was a group from Antoniadis and Mark Asachi and also Bill Wakeham. So they also are saying the same things about a lot, because it's needed a lot of care when you are talking about a measurement of the thermal conductivity of nanofluids. So I will go to our tests. So our tests revealed an increase in thermal conductivity when nanoparticles are added, while the best results were attained with the addition of magnesium oxide, data being recently published in Thermal Science and Engineering Progress, also by the end of last year. Here are some comparison data with different nanoparticles between our several experiments, and also you have here on the right hand side a diagram that is outlining the relative thermal conductivity over temperature, and you can see that the addition of nanoparticle is increasing the thermal conductivity, not much, up to 10%. But over the temperature variation, the thermal conductivity remains almost constant, and this is due to the behavior of polyethylene glycol that has a constant thermal conductivity up to higher temperatures. The results are similar also for titanium oxide. So it is clear that the temperature influence on thermal conductivity is not significant for any of these samples, and I may say that also for other samples that we tested. Because the increase in thermal conductivity is situated about up to 1% if compared to the values registered at ambient temperature, so this is not relevant. As a conclusion from our experiment with nanofluids based on polyethylene glycol 400, many of these things I already said, that the thermal conductivity of the base fluid is not influenced by temperature variation, and the thermal diffusivity decreases at temperature variation, while its variation for each suspension depends highly on the nanoparticle type and concentration. In terms of thermal effusivity, I will present few experimental on several mixtures, this time between PEG 400 and PEG 200. The experimental that we are pursuing right now, then the results are recently published in Molecular Liquids. It's not written on this slide because it was just arrived 2 days ago, the acceptance of the manuscript. So our idea was to establish a new host fluid for future nanocolloids and to combine the advantages and disadvantages of two low molecular mass PEGs. It is about PEG 400 that has a very large, very high stability, thermal stability, but higher viscosity than PEG 200. And we thought that a combination between these two can go to a better heat transfer fluid. So the results showed that the theoretical estimation, you can see that figure with experimental and rule of mixture. We wanted to show very clear that the theoretical estimation of thermophysical properties of fluids, and it's not always the most appropriate approach, and experimental is the best way for accurate data on that. So you can see on the two graphs that the thermal effusivity of the mixtures are between the effusivity of the base fluids. As a conclusion, we can say that both thermal effusivities for PEG 200 and PEG 400 highly depends on their molar mass, while PEG 200 has larger thermal effusivity than that of PEG 400. And based on the results that we previously discussed and other results that are not shown here, we decided that the fluids F3 and F4 are the best choice for new nanocolloids, and at this point are employed also in a larger nanocolloid study, but the experimental is ongoing. So at the end of my presentation, yes, I'm coming to the end of the presentation. I can say that I'm happy with the C-Therm equipment due to data reliability, accuracy, and we love the software. Here you can see several pictures from our lab that is also available online. The lab is at Nano. And future details about our ongoing project, FluidX app, are also online. The FluidX app main scope is to develop and foster the use of nanofluids as advanced heat transfer fluids to increase the efficiency of heat exchange application. We have a large project that started this year in January and will end at the end of 2027. So I will close my presentation with a quote, strive for perfection in everything you do. Take the best that exists and make it better. When it does not exist, just simply design it. This is not myself, this is Sir Henry Royce. I am Alina Minea from Gheorghe Asachi Technical University of Iași in Romania. Thank you for listening to me. Thank you. I'll stop share the screen.
Awesome. Thank you very much for that presentation. Yeah, so folks, I'm just got a couple final little outro slides here. I've noticed there are some questions being asked for the Q&A, so we will get to those here shortly. But yeah, just wrapping things up here today. So as a note, like I said, today's webinar, as well as all the webinars that we put on, are available on our website for review. So certainly feel free to check that out. Also, some of the technical content, paper, links to the papers, these can also be found on our website if that is of interest. I'll give a little plug for our LinkedIn for folks who aren't already following us. That's going to be the best place to keep up with any upcoming events, content, additional webinars coming out in the future. So if you like to keep up with what we're doing here at C-Therm, please give us a follow on there. I will mention the next webinar that we have scheduled is May 15th. This is going to be on inline quality assurance of sediment detection in 2K polymer adhesives with thermal property sensors in dispensing equipment. So this will be similarly we have a few guest speakers joining us to talk through how this is being incorporated into some of their dispensing applications. I'll also mention some just events. So I guess, yeah, happening right now, the Thermal Management Expo North America. This is in Novi, Michigan. I have some colleagues that are currently down at the show. If you happen to be in the Michigan area, if you're planning to stop by, you're interested in maybe chatting about thermal conductivity or other material characterization, we are at booth 410. Definitely feel free to stop by there. We'd love to have a chat. Also, later in the summer, July 24th, there will be a materials characterization showcase. This is being held in Houston, Texas. So again, if you're in the area, keep an eye out for more information on this event. And with that, that brings us to the end of our official session here today. Once again, I would like to thank our guest speaker for joining and presenting with us. It is much appreciated. For those of you who are interested in staying on for the Q&A, at this point, we're going to end the official recording. So if you have to drop off, thank you for joining us here today. But again, if you are interested in sticking around, we are going to go into the Q&A session here shortly. Thank you, everyone.